Hi everyone, welcome to the presentation of our paper FLD Plus Data Efficient Evaluation Metric for Generative Model. My co-authors are Neeraj Nixon and Professor Amit Sethi, and we are from Indian Institute of Technology, Bombay, from India. There are numerous image generation models that are coming in the market today, but the evaluation metrics for this model is currently inefficient, because assessing the realism of generated images is a very subjective and hard job. An ideal metric should have monotonicity with increasing levels of image degradation. It should be very reliable, as in it should give a reliable value for the metric with a very limited number of samples, and the computation should be very efficient. The most popular metric currently in use is FID, and it has many limitations. FID calculation relies on a normality assumption which does not exist for real image distributions. For example, if two different distributions have same mean and same standard deviation, the FD distance computation will give zero value even though the distribution actually looks different. It also needs at least 20,000 real and generated image samples to give a reasonably stable metric value. And also, the previous work have shown that FID is not a monotonic metric to image degradations. So we use normalizing flow to actually map the probability distribution of the real data and compute the actual likelihood of the images with respect to the real image data. So we train the normalizing flow using real images where we extract the features of the pre-trained ImageNet backbone, do average pooling and flatten the features, and then train a normalizing flow on those features and compute the log likelihood. Once we train the normalizing flow or the entire model, the flow model, we pass the generated images and real images through the flow model and compute the log likelihood of the images, both generated and real, and compute the ratio to get the FLD plus metric. This is an improvement over the previous metric because the FLD metric or the flow-based likelihood distance metrics directly trained on the normalizing flow, and that is an issue because the latent space has to be the same dimension as the size of the image, and because of that the computation was actually much larger. But since we actually reduce the dimension of the image by passing it through an ImageNet pre-trained backbone and flatten it, we are reducing the latent dimension and still training the images on a smaller normalizing flow to compute the likelihood. The core idea is that once we train on the real data distribution, a real sample will give a very high log likelihood. If the generated distribution is similar to the real distribution, then the generated sample will also be lying somewhere near, and the log likelihood of the generated distribution will be quite similar to the log likelihood for the real distribution, real images. But if both the distributions are separate, then the real images will still give high log likelihood, but the generated images will be giving a much lower likelihood with respect to the real distribution, because the normalizing flow is trained only on the real distribution. And the ratio will be different in both cases, which we can use as a reliable metric. So the figures show that FLD plus is a good metric in terms of monotonicity to various kinds of image degradation. Compared to FID, which needs around 20,000 images for settling to a stable value, FLD plus just needs around 200 samples, which is useful for data scarce domains, and it is much faster to compute than FID. We have shown in our experiments that it works well with large models like Stable Diffusion and StyleGAN2. To conclude, we find the limitations of the current metrics like FID and introduce a new normalizing flow based metric which have improved efficiency by a reduced latent space, which is monotonic to image degradation, works with diffusion noise, and is much faster to compute and is data efficient.